recording. Okay, so the session is being recorded, which is that means I'll post it later on on YouTube on my website. So they want the first question. He wants you to compare between X-rays and MRI, and he wants you to explain the main differences. So he wants at least 3 points. Let's make sure that we cover the main ones. So point number 1 is simply the origin. So this is X-rays are based on accelerating or generated using accelerating. So generated X-rays are generated by accelerating electrons, charges or electrons. Yeah. So that's what the first one. Now, on the other hand, MRI is generated by exciting protons. Okay, protons. So that's the first main difference between the two. So he wants you to mention three differences. Difference number 2, that X-rays are ionizing, and MRI, of course, is not ionizing radiation. So that's the second comparison between the two. The third one is that okay. So we covered the first one, which is basically the origin or the how are they generated. 2, we covered the ionizing effect, and 3, point number 3, it's basically the application. So one of them is considered dangerous or harmful. Well, that's X-rays. So X-rays are harmful, and while so X-rays are harmful, while MRI is not harmful in terms of the biological effect. So these are the main three points that that you need to mention. Now let's go on to question 2. Anybody has any questions? If somebody has a question, then you can actually speak if you want, or you can just write your comment. So any questions? Okay, so I'm assuming there are no questions. Okay, so but you hear me, right? We can't hear you. Can you hear me now? Yes, okay, there are some. Yes, okay, good. So did you hear me? Did you hear the whole question? So question one is okay? Okay, I think we answered that. You can proceed. Okay, thank you. Okay, let's go to question 2. Question 2 says that a particle is actually is moving. The particle is carrying 50 microcoulomb. So the charge Q is equal to 50 microcoulomb, and it's moving with a velocity V is equal to 2, right, along the I hat direction, and it's moving in a uniform field B, which is equal to minus 6.7 in the J hat direction. First of all, what is the force on the particle? And then he's asking you another question. Okay, let me get, sorry, let me get, where is this? Yeah, let me get a whiteboard here. Oops. Okay, so what we need to do, this is what we need. F is equal to Q V cross B. That's what we need to do. And F, of course, is a vector. right? Okay, so now I need to do the cross product there first, and he told me that V is simply 2I hat, okay, and B is minus 6.7 J hat. So that means I need to cross the I hat with the minus J hat. So if you remember, we said in order to do the cross product, I have to do the following: 2, 0, 0. That's the I hat. That's what the I hat is. And then I repeat the first 2, 2, 0. And then for this guy here, 6.7, again, I have to do 0 minus 6.7, okay, and 0, and then 0, 6.7. So I'm taking the vector I hat, J hat, K hat, and then I repeat I hat and J hat. That's what I'm doing now. The first one here will give me this multiplied by that. That's 0. So the I hat is 0. And then if I take this guy, this also 0, 0, that's 0 in the J hat. And yeah, and in the K hat, remember this is negative. So 2 minus 2 multiplied by 6.7, that will give me 13.4 negative. So my result then for F, the magnitude of F, or the vector F, is equal to Q multiplied by minus 13.4, and this is the K hat. Remember, this is the I hat, this is the J hat, and that's the K hat. So K hat. So where is it? It's along, or sorry, the Z minus Z hat or K hat, depends on which one you use. So again, if as a vector is equal to Q, the charge, multiplied by minus 13.4 along the negative Z direction, okay? That's what my force is. So the force is equal to minus 13.4 multiplied by the charge, which he told me it's equal to, I forgot, what is it? It's 50 microcoulombs. And it's along along the negative Z direction, okay? So let's go back to this one here, okay. So what does it tell me? It says that find, so that's the first one, that's part A is done, which is finding the force on the particle. Point B, now all you have to do in this one is just you substitute for Q, and then you get the answer, and it's along the negative Z direction. Point B, from the dot product, if dotted with V and if dotted with V, show explicitly that the force is perpendicular to both F and V. Now remember, let me go back to the let me go back to this one here and share a whiteboard again. Now remember, the force F was equal to along the negative Z hat, whatever the number is. There was a number here, but it's minus 13 point, what is it, 4 times 50 microcoulombs. So that's my force. Now he wants me to show that if dotted with V, right, and if dotted with B are equal to 0, right? That's what he wants. What he wants me to show, right? The voice is cutting. Okay. Now, how is it now? How is it now? Somebody, just in general. How is the sound now? Voice. Is my voice okay? Yeah, it's fine. Okay. All right. So good. All right. Thank you very much. Okay. Now, okay. So now what I need to do, I need to show that this. Now, I know from my definition of the dot product, if dotted with V, it will be simply F V cosine the angle between them. Now, remember, V was along I hat. This guy here was along I hat, right? and B was along J hat, right? Or along the J hat directional. So if I wanted to multiply, for example, this, F and V, F is along the Z hat, right? And V is along the I hat. What is the angle between them, right? This is my X, Y, and that's Z. So this is my I hat, this is my J hat, and this is my K hat. So if you look at the angle between, for example, K hat or Z hat and I, this one is 90. So cosine 90 is equal to 0. And therefore, F dotted with V is equal to 0, and that indicates that the angle is 90 or perpendicular. Similarly, if you take the force which is along here, so this is my force, F, and this is my V, and this is my B. If I take the force dotted with V, the angle between them is 90. If I take the force dotted with the B, the angle between them is 90, and that gives you 0. And that's your answer. Okay? All right, so I'll give you 1 second or 1 minute to take a picture. As I said, this is recorded, so don't worry. I'm going to post this after we finish. All right, so let me go back again. So that answers part B. Now, let's see what he wants in part C. Okay, doctor, repeat how you find the angle. How? I will do that. Okay, somebody is asking me to repeat how I found the angle. Okay, let me just erase this. For that, I need to erase it though. Okay, I'll erase that. So remember what it looks like. Yeah. So this is my X, Y, Z. This is X, this is Y, this is Z. Okay, so this is X, this is Y, this is Z. This is my I hat, this is my J hat, this is my K hat or Z hat. Okay, it's either I use I, J, K or X hat. So this is X hat. Okay, all right. So okay, so this is it. Now, as you know, the angle between this will give me this is my force, this is my B, and this is my V. He told me that V is here along I, and B is along, actually, in fact, it's along negative I, okay, because this is J, negative J hat. So somewhere here, B is somewhere here, not there, okay? So that's my B, that's my F that I found, and this is my V. The angle, as you can see, the angle between these two guys is 90. The angle between these two guys is 90. The angle between these two guys is also 90. And that's how I found the angle from the X, Y, Z. So the angle between V and F is equal to 90. And the angle between, F and B is also 90. Just from these guys, from this definition here, where this is, as I said, this is my K hat, that's F. And this is my Y hat, and that's minus Y hat. Here, that's my B. And this is my V, which is along the I hat direction. Okay? So the angle between this guy, well, I need V and F. So V and F, that's this angle here. That's 90. And then F and B, that's this angle, which is 90. I think that's clear, okay? All right, let's move on. Okay, so let's get back to the questions. Let's get back to the questions here. The third one, okay, the third question, or the third part, C. If there is an electric field E, which is along the negative Z direction, what will be the net force? Okay, so we know that F net will be equal to F the magnetic field plus F of the electric field. Okay, sorry, the electric field. He told me that the electric field, this one is plus minus, because he told me it's a negative z direction, 3 newtons per coulomb. All right? No, 3 newtons, and it's the charge. It's okay, 3 newtons per coulomb. Let me go and get again a whiteboard. So this is the 3 newtons per coulomb. Okay, so he needs F net. F net is equal to FB plus FE as vectors. Okay, all vectors. Now this FB is equal to, we just calculated it, is equal to QV cross B. We calculated that, which is equal to Q times 13.4, and it is along minus Z hat directional. And then the electric field, the force, FE is equal to Q multiplied by the electric field. Okay, the Q, he told me it's 50, so Q multiplied by the electric field, which he gave me, it's, I forgot what it is, but it's something multiplied by, I don't know, 2 or something, the electric field, right? And it's also, again, Z hat. So this is Z, and this is Z hat. I can simply, add these directly, and then just calculate, put Q here, the 50 microcoulomb in here, and over here we have, okay. So this answers that question, which is basically, as I said, this is a very important question, and I'm very sure one way or another I will repeat it in the quiz on Monday. So definitely you will get a question like this for sure, if not the same question. All right. Okay. So let me just go back and see if there are there any questions or any concerns? Should I just keep going, because we taken a little bit of at least longer than what I expected in the first 2 questions. Okay. All right. So I'll just keep going now. Question number 3. Question number 3. This one here. Okay. So question number 3 said he asks you to calculate the Larmor frequency gamma. He gave you gamma is equal to 42.6. So gamma is equal to 42.6 megahertz per Tesla, and then the magnetic field is equal to, let me just erase that. So the magnetic field is equal for 2 magnetic fields. For magnetic field is 1.2, and the magnetic field, the other one is 1.6 Tesla. Using the result, okay, find the Larmor frequency. Okay, let me just go and again do and find another. Okay, another whiteboard again. So we know that the frequency, the Larmor frequency, F Larmor, is equal to gamma multiplied by B. So let's call F1 FL1, which is equal to gamma is 42.6 multiplied by the magnetic field, which the first one is 1.2, and that's your answer. Okay. The second one, F Larmor 2, is equal to, again, 42.6 does not change, and that is multiplied, the other one multiplied by 1.6. Yes, let us finish. Yeah, the quiz is on Monday. Yeah. Okay, so that's this, and this. So you just calculate these two. All right, that's the answer to your question. Now, the second question he's asking you, and that's the important one. The second question he's asking you, oops, where is this second page here? The second question is asking you, using the result in part A, describe the significance of the Larmor frequency in MRI. Okay, so what is the significance of the Larmor frequency in MRI? The significance of the Larmor frequency in MRI is it is determined to it's used to determine the frequency of the radio frequency, or the operating frequency of the RF. Okay, so that's what once you find what your F Larmor frequency is, then that's what you turn, or what you set your operating frequency of the external RF electromagnetic field, the resonance frequency. I said the radio frequency. So that will be let's write that down. It is used to set the value of the resonance frequency. Okay, that's what it's used for. Okay, if we go to question number 4, describe the role of the gradient fields in resonance imaging. This is something, again, definitely you will see it on Monday. Okay, so let's see. Well, he wants to know the gradient field B. Yeah. Now the question, if you remember, the answer, or the way we set this up, we said that our magnetic field B total will be equal to B0 plus delta B. Okay, and delta B is my gradient field, magnetic field. Okay, my gradient magnetic field. What does that mean? That means when I set my patient here, okay, when I set my patient here, the magnetic, this is my B0. B0 has some value, I don't know, 2 Tesla, 1.2, whatever it is. And then my gradient field will, this is the patient, this side, my gradient field will vary across the patient. This is what my delta will be simply this. So this value here, this value here, this value here, this value here, this value here. That's what my delta is. So if you wanted to describe the significance or describe the gradient field is used to vary the field across the patient, right? Across the patient, the long axis of the patient, across the long axis of the patient, to enable us to select where to image or view. Okay, so that's what the gradient field does. It's enable us to look at a specific point here, and we'll see it in one of the examples that I've added today. All right. Okay, so let's go back to the second question, or the next question. Okay, we've done that. Okay, now question number 5. This is the question that there is quite a bit of calculations. Well, actually, it's not quite a bit of calculations, but you need to do some calculations in order to understand this. Now, what is he doing? It's saying, using the following expression for relaxation times T1 and T2, find and define the physical meaning of both T1 and T2. Okay, so he wants you basically to use these two equations. The first one is saying that mz is equal to m0 1 minus e to the power of minus t over t1, and the other one is saying that mxy is equal to m0 e to the minus t over t2. He wants you to use these two equations to find and define what is T1 and T2. That's what he wants you to do. Now, let's see how we're going to do that. Let's go back to the whiteboard and see. At least I'll do one of them, because time, well, almost half an hour, and we have a lot of things to do. Okay? Now, let's take the first one. So that mz, right, is equal to m0 1 minus e to the power of minus t over t1. Remember what I need to, I want to find and define. Now, to find t1, set t, the time, is equal to t1. Okay, capital T1. Okay, find it, it's equal to t1. Right? If you do that, then mz, right, is equal to m0 1 minus e to the power of minus 1, because t is set to be equal to t1, right? 1 over e, we said it's equal to what is it, 0.37 or something like that. Okay, that's what it's equal to, because that's e to the power of minus 1 is simply 1 over e. Right? So this is equal to M0, 1 minus 0.37, which is simply 63, 0.63. So this is equal to M0 multiplied by 0.63. Okay, so I found that he said find and define. So I need to define. I found that I can just say it and you guys can write or record. Now, this tells me that T1 is the time needed for the for MZ. Remember, this is what MZ is 1 minus. So it will be something like this one here, right? That's what this looks like, right? So he's telling me that MZ at T, when T is equal to T1, when T is equal to T1, then the magnetization, the longitudinal magnetization, has grown to 63% of its initial value, has grown to. Okay, so let's do this again. Okay, let's write this again. So we found what MZ is equal to when T is equal to T1, and define T1. T1 is defined as, okay, T1, again, T1 is the time needed for MZ to grow back to 63% of M0, and that's it. Okay, so that's fine and define. You can do the same thing for the other one, for MXY. You can do the same thing for MXY. Let me just okay, let me just do it again. So MXY, right? MXY is equal to M0 E minus T over T2. So do the same thing, set T2, set T equals to T2. And then from there you have MXY is equal to M0 E minus 1, which is equal to 0.37 M0. So you can say that T2 is simply, T2 is the time needed for the transverse magnetization to decay to 37% of M0 or its initial value. Okay, that's it. As I said, please don't worry about writing, because eventually we will eventually you'll have the video, the whole video recorded and posted on the website. Okay, all right. Let me go back, because as I said, I mean, we're running out of time. We need to, oops, wait, what is this? Okay, let me go back and see because there is one question that I really want to go over, and that's something that probably will be in the final, that you'll see in the final. So, okay, so let me, we've done this, we've done that. Before I go, he asked you to sketch. He asked you to sketch, right? Sketch the graphs. So remember, for T1 and for T2. For T1, it's something like this, right? The maximum value here is M0, and for T2, it's something like this, and it starts from M0. And this is your saturation, and that's your saturation here. You have to somehow, this is your 0, and that's your this is your infinity somewhere. And in both cases, you have to show where the 63% is, or where the 37% is. Okay, so this will be somewhere 63% right here, and this will give me the point here is equal to 37%. Okay, make sure, because as I said, I mean, this question, all of these questions, either you will see them in the quiz on Monday, or you will see them on in the final on January 7th. Okay. I'm going to leave question number 7, because question number 7 is very easy. He gave you F. We know that F is QV B sine theta. Where did I get this from? This is Q V cross B, right? And the cross product, when you want to, the magnitude of the force F, is simply you say QVB and sign the angle between them. If you look here, he told you that the angle between them, or you know that the angle between them is 90, and then this will be equal to 1, right? And then the force will be F is equal to QVB. And if you're given F and VQ, you can find what the magnitude of the value of B is. Okay? Let me just very quickly go over some of the multiple choice questions. And if we have time, we can come back to these questions in more detail now. So the question number 7 says that in MRI, the gradient fields are used to do what? Are used to maintain uniform magnetic field? No. Are used to estimate, eliminate the magnetic perturbation? We don't even know what the perturbation is, so forget it. It's not it for sure. Shorten T1. There's nothing called about shortening or increasing T1, because T1 and T2 are constants. Remember, maybe I did not emphasize this in the class, but T1 and T2 are constants for a specific tissue. Provide spatial localization. I don't know if you guys, if you can pick up the language here, but this is the right answer, to provide spatial localization. Spatial, that means over space. As you move across space, then he wants you to provide localization, spatial localization. That means he will tell you where exactly to look, okay? Meaning that every point across the patient, this is my patient, right? Every point across the patient has a different magnetic field, remember? So that's what it does. So this is the right answer. D is the right answer. Provide spatial localization, right? The last point, measure the proton spin. No, it does not do that. Okay, question 8. In MRI, the following two statements, okay, the following two, when placed in an external magnetic field, protons move in a particular way called precession. It's true. And 2, the Larmor equation indicates that the precession frequency is proportional to the magnetic field. Okay, so now he's telling you, are they both true? Are they both false? And one of them is true, I is true and 2 is false, or 1 is true and the other is false? Can somebody just, if I take some of you here, I'll go back to here, and can someone give me the answer here? Okay, someone give me the answer here. Is it both true or both false, or A is true, B is false, or so forth? Can somebody tell us the answer? I'm going to look at the names. Diana, what's the answer, Diana? What's the answer? Are these two statements true? Guys, do you hear me? Okay, now I'm asking, about the question that I just mentioned. Okay, the question I just mentioned a few minutes ago, or a few seconds ago. Okay, let me go back to the question again. I just want to see, get some of you to interact. Okay, so it's this question here that I was asking about. Okay, question number 8. Okay, question number 8. What is the answer to question number 8? I think I asked Diana. I can ask somebody again. I just picked up the first name I saw. Okay, A is the answer? Yes, absolutely. Both statements are true. Okay, A is the answer, is the correct one, A, right? Because it is true. Yeah, Diana, absolutely. So both answers, Mariam, A, excellent. All right. I should next time to have some bonus marks for that. Okay, now let's go to question number 9 and see if some people can get that. Okay, if you reduce the wavelength of an electromagnetic wave, radio frequency wave, EM, wave starting, where is it? On a string by half. What happens to the speed of the frequency? Okay, let me just give you the formula, and then I will ask again. Okay, so V is equal to lambda F, right? Now remember, for an electromagnetic wave, this is constant, C. C is equal to lambda F. Okay, now what happens? Okay, now if you reduce this, so he wants to compare the speed of the what happens to the wave speed and the frequency. Okay, now the speed, I have to now limit my answer to C and D, because for an electromagnetic wave the speed stays unchanged. So that means it's either C or D. The others, A, B, and E, they're not going to be true, because this is an electromagnetic wave and the speed does not change. Okay, now let's look at now to the frequency, because let's write it in terms of lambda is equal to C over F. If F, what do we do? Say lambda. Okay, lambda is reduced to half, so that means I need to do F. F is equal to C over lambda. Right. If lambda is reduced to a half, that means it's 1 C over a half. That means it will be 2 C. That means it will be double. Okay, the answer is D. Absolutely correct. The one who said the answer is D, absolutely correct. Okay, but you saw how I did it. Remember, this is a worksheet. I need you to show me the calculations or the answer. So it's not just you're gonna circle D and go. Okay, is that clear? All right. So let's erase and then keep on going. Number 10. An MRI system creates an image when. Okay. So now this is again. You guys have to answer this. One of you has to answer. I just read this. All the hydrogen atoms in your body line up, creating an outline. Or hydrogen atoms facing opposite direction cancel each other out, creating a transverse outline. The hydrogen atoms go back to their normal position, releasing energy. Okay. Sorry, it's the same. I'm missing an answer. This is something. It's okay. Let's take this out until I fix this. So take this out because it's missed the answer. The correct answer is I forgot to copy it up. So this is out. Yeah, let's take it out. Thank you, Miriam. All right, so let's go to question number 11. Question number 11, the application of an RF pulse causes the protons to precess. What does that mean? Can somebody answer that? Does it mean it spins in a reduced velocity? Does that mean it spins? It is the proton. It begins to spin in a possible in the opposite direction. It starts to rotate, wobble about its axis, or it spins. Absolutely. Diana said C. It's C. Right. Absolutely. Okay. So the answer is C. Okay. Let's move on to the next one. This is the question that it's very important to understand how to do it, and it's straightforward, but you need to understand how to do it. Now, if the external, question number 12, if the external field, so B is equal to 2.4, B is equal to 2.4 Tesla, right? Find the gradient field needed to examine the 3 regions, slices that are given. So this slice here, this slice here, and this slice here. Now, the slices, as you can see, they are defined by the frequency. One of them is 64.001, and the other one 64.005, and the other one 64.008. Okay, these are the 3 frequencies. Now he wants you to find the gradient field. Okay, let me just write these down. By the way, guys, don't sign out because I just saw the number of students is few. So at the end, I'm going to write down the names and I'm going to give you a bonus. So please don't leave. Don't leave until we finish this, and don't leave before I write down the names, because I have all the names listed in my screen here. Okay, so okay, let me just write down 64.001, 64.005, and 64.008. These are, and the external B0 is equal to 2.4. Okay, now he wants to calculate or find the gradient field. Okay, so let me just go to the whiteboard here. Now we know that B, right? We know that B total is equal to B0 plus, okay, B0 plus the gradient field delta B. Okay, that's what the total magnetic field. Now he told me that this one here is equal to 2.4. This is 2.04. Okay, plus delta B. Okay, and this is B total. Okay, so that's what he told me. This is 2.4. Now he wants this. Right? He wants this one. Now remember what we said. We said that B, the Larmor frequency FL is equal to B total multiplied by gamma. Okay. Now I have B total. For example, if I take the first one, 64.001 is equal to B total multiplied by gamma, which is 42 point, I don't know, forgot, is it 0.6 or some, I don't know, maybe 42.6 or anyways, gamma for hydrogen, so we know it. From here, I can calculate the total and then take it over here. I substitute it, and then from there I get my delta B, and that's the gradient field. Okay, so the gradient field delta B will be equal to B total minus B0, and B total I calculated from the Larmor equation, right? The Larmor equation, knowing gamma is a constant and B total is the one I need to calculate. So here I'll have B total is equal to 64.001 divided by 42.6. Okay, and then I substitute for that, and that's it. Okay, that's the answer to all of your questions. I believe that was the last one. And as I said just before we leave, let me just write down the names, and I'm just going to say them. Okay, Aisha Husay, okay, Diana, and Gharisa, okay, and Malak. Just make sure that I say your name. And then Malath, and then Marwa, and now Maryam, number 3. Who is Maryam? Because I have a number of Maryams. Okay, what's your last name, Maryam? Maryam, number 3. Okay, Maryam Ali, Al-Ali. Okay, Maryam Ali, Al-Ali. And then I have Reem. Okay, we have one Reem. And then Saba, we have one Saba. And then we have Thelini. Okay, we have one. And then Yasmin, we have one. Okay, thank you very much. Jazakumullah khair and good luck. Anybody have any questions before we close it? Anybody have any questions? Okay, so good luck. And okay, thank you. Good night. Okay, good night and enjoy your weekend. Okay, yes, it will be on YouTube. I will post it on YouTube as soon as I'm done. All right, thank you very much. Okay, let me stop the session here. Okay, stop recording.